microphone. It would be better for me because I have to take care of also particularities with the microphone. Ladies and gentlemen, first of all, I like to thank the organizers of this nice conference, of this nice school, in particular Professor Cicic and also Professor Mihel for this kind invitation. I'm very glad to be again here, and I would like to thank also those who contributed to this conference. In particular, I like to mention that my lecture, which I like to present, is not such a fundamental lecture as we heard this morning. Of course, it was a beautiful lecture by Professor Bunkov, but this is the high physics, this is the top physics, this is like the summit of the physics. I am walking in the valley, and it's not so exciting, and my contribution is more or less a practical application. Of course, there is some mathematics, and I hope that you may understand that the understanding of the formula is not so important. I try to convince you about the idea, and the idea is not so very complicated. I'm very glad that Professor Cicic in this morning also mentioned the very important contribution from the St. Petersburg physicists to the field of NMR. I always am very interested that all these important contributions which have already forgotten will come to the light, because without these very important contributions from the past, we are not able to make any progress. And so far it was also very interesting to listen to Erwin Hahn, to have a personal impressions of his personality. Ladies and gentlemen, my lecture is devoted to NMR methods. In particular, the aim of my lecture is to combine magic angle spinning in heterogeneous system with a selective measurement of diffusion processes. This is an idea which was realized in Leipzig. Of course, it is based on the knowledge of the particularities of molecules adsorbed in interfaces, and this is related to the fact that in interface we have very ill-defined, inhomogeneous local magnetic fields. This is the first topic. Second, of course, I should mention that we have a lot of work with respect to diffusion studies. This is the work by Professor Jörg Kerger mentioned below, and also I should not omit as fundamental contributions from the group in Ljubljana, in particular Professor Janez Stepisnik. This is the basic, although I cannot mention always the important contribution from their work. So I will focus to the combination of magic angle spinning and pulse field gradient techniques. And the main important is, in my contribution, to understand the influence and the role of the inhomogeneous local magnetic field and the establishment of the gradient fields. It means our problem, and this is already the whole story of my lecture, is to create such internal gradient fields that the direction of this gradient is just along the axis of a magic angle. It means a very simple idea. We have a magic angle, I will define it, and we apply a rotating magnetic field gradient just along the axis of this rotating field. This is already the summary of my lecture, but now, excuse me, I will try to go step by step in a, I hope, not so complicated way. It means I am dealing with porous materials. This is well known. We have silica. The most important point in this way, it's also the work together with Professor Czarnaya in the fifth fact, is that we can define the surface area, but also the volume between these shares. We have porous aluminium, we have zeolites. You know these materials. The most important point, which is also important for this lecture, is that we have very well-defined internal voids. You see the diameters, it's nano size, 12.7 angstrom, and we have also single crystals, ensemble of small crystals, which allow a better estimation of the local field. And finally, in Leipzig, there are some very important works from between chemists and also Professor Hase, who has now my chair. And in this case, we are investigating also metal-organic framework. I have already presented in this conference some results about NMR in this metal-organic frame. I do not go into details. I only would like to mention that also this very interesting class of compounds belongs to the system which we have studied. And also in this case, you know, we have well-defined internal voids, and you see on the left part on this transparency the diameter. This is between 5 and 9 angstrom. It means we have a molecular dimension, and this is a very interesting material. And the people believe that this crystalline and porous, well-defined three-dimensional structure plays an important role for a very interesting chemical process. But you see, in comparison to the zeolites, the stability of this metal-organic framework is not so high. And now is the question, how is the progress in this field will lead to much more stable materials which can be used. It means this is a methodical background. In all these systems, including also membrane systems, this is a former co-worker who is now working in the Max Planck Institute of Cognitive and Neuroscience. Unfortunately, he did not continue with this work in Leipzig. We have also the problem that we have inhomogeneous local fields, and we have a problem with applying the techniques of solid-state NMR spectroscopy. And of course, very interesting is the measurement of diffusional processes using bulk field gradient techniques. This is the background. To come to the physical problems, I have to tell you briefly. We have a limited resolution in heterogeneous system, and this resolution is in most cases not related to the reduced mobility, but is related with the fact that we have a strong distribution of internal fields, and means the most important that we have inhomogeneous magnetic fields in the holes and in the system. It means if we try to have a gain in the resolution, we have to deal a little bit more precise with the magic angle condition. As you see, the normal magic angle spectroscopy is related with the fact that our interaction Legendre polynomial of second order, and this famous formula 3 cosine square minus 1 equals 0 is well known. This is a magic angle. But in our case, the local magnetic fields are not only described by Legendre polynomials of second order, but we have a lot of further terms, and of course magic angle does only hold if we have second order. It means we have a problem, and this problem is not so well defined because our distribution of local magnetic field depends on many factors. This is a physical problem we try to circumvent, and of course we try to circumvent this in different ways. First of all, I will show you a typical example. If we have molecules attached to membranes, normally you have a spectrum which is not well resolved to see the spectrum on topic. And our problem is, of course, to reduce the influence of the magnetic field in order to come at least to the chemical shifts of the different parts in this sample. And I show you a simple example. We have a static sample, we have a magic angle spinning, also the conditions are not optimum, and you see an important improvement. And this is not related with the mobility, this is only related with the inhomogeneity of the local fields. in this material. It's a whole story. If you now are speaking about nanoscience, many of the systems are characterized in the same way. It means by such local inhomogeneities. The problem is the following. We have to understand in this context the role of the magic angle spinning, but this magic angle spinning in this system is also depending on the internal mobility. You see, we have a resolved spectrum, and you better know than myself that the constitution, the different components in this system, lipids, small peptides, are still mobile. And now we have a problem. On the one side, we have the coherent motion, which is introduced by magic angle spinning, and we have an incoherent motion, which is caused by the local, still appreciable molecular motion. This is our problem, and therefore we need to understand in the first sense the role of magic angle spinning in relation to the thermal mobility. I have shown here a typical example. This is a sample in which we have adsorbed molecules like butene in zeolites, and these systems are very interesting for chemical reactions for catalysis. I do not touch the problem of this application of this technique. I only will mention that we can resolve the spectra in a better way. I have shown you the molecule on top. We can see each resonance lines only by applying magic angle spinning, and already the fact that some parts of the local magnetic fields are proportional to the Langchamp polynomial of second order, like seen below. P local is equal constant times this magic function. This leads to an appreciable resolution, but this resolution depends not only on the frequency of this magic angle spinning, but also on the thermal mobility. Of course, everybody of you knows if we apply magic angle spinning and we have low rotational frequency, like seen here, 200 Hertz, 1200 Hertz, we have side bands, you see on top. We have influence of the rotational frequency, and this influence is also determined by the residual thermal motion. You see, in this case, we can have a nicely resolved spectra having a rotational frequency of 1 kilohertz. I will show you another sample. You see, this is a cysteine ethylene glycol adsorbed in sodium X, and you see these molecules also in the adsorbed state are class-forming molecules. It means you have in the work, for instance, of Professor Spies, you can use these molecules in order to have class-forming properties. And you see, in this case, we have also very low frequency in order to have resolved spectra. But if you look now at these molecules in sodium X, you see we need rotational frequencies up to 10 kilohertz in order to have a well-resolved spectrum. The summary of this story is the following. You have heterogeneous system. You understand the role of magic angle spinning, but we have in a coherence between this coherent motion, as I already mentioned, and the statistical motion. Coherent motion is advantageous for us. The incoherent local motion does not give good results because this incoherent motion is in competition with the coherent motion. And therefore, our first problem was to understand the connection between molecular motion and the rotating samples, in particular in those systems, and I have shown you now the sample, when the number of molecules in these nano cages is so small that we have in some cases only one molecule per cage. It means we have a system and we can prepare samples in which in each cage of this material we have only a single molecule. It means you have a very tight adsorption of this molecule, and this leads to the fact that we have very carefully to check whether the influence of rotating motion, it means spinning sample motion, or the influence of thermal motion is important. And only with this knowledge we can understand the different systems. On the left side, soda light, one molecule. We have here in this silica light, we have an internal dimension of 0.3 angstrom. It means 0.53 nanometers, and we have a very small number of molecules. We have very interesting zeolites like Alpo zeolites. These are long channel systems which are used in the chemical industry for petrol reforming, in which the channel of molecules. It means we have different systems in which we have to solve the question of magic angle spinning and thermal motion. The ideas are already very well known. We have first very nice work in Novosibirsk by Professor Mastirin. Unfortunately, he already died. He was the Institute of Catalysis, the famous Novosibirsk Institute of Catalysis. They applied this technique, and they, together with Freude in Leipzig and our work, they used vacuum-tight magic angle spinning tubes in order to have very defined measurements in case of adsorbed matter. It means our program is to understand the coherence between MRS and the influence of the incoherent thermal motion. Of course, the problem is to understand also the averaging mechanism of the locking fields. It means thermal motions means, in our case, we have a displacement of the molecules during the time scale of the NMR. It means free induction decay, and this displacement is only essential in case of these systems if the mean square distances are comparable to the size of the microcrystallites. It means we have a process which is really not determined by local motion, but by a transportation of these molecules through the dimension of our zeolites. This is something like micrometers. But you understand, we have now a problem. In our cages, the molecular processes are in cages which are of nanometer size. But the averaging processes we have is not nanometer size, it is micrometer size. It means we have to understand the different time scales in order to understand our experiment. I will show you an example. Here we have developed a theory. It's based on the earlier work which has been formulated by Anderson and Weiss. This is a theory which has been established already in the 1960 years. It's a well-known theory described in the famous book of Abraham. I will not mention this. And we have simply extended this mean field approach, not the multiples approach, which is very useful for all the biological applications, but it's a relatively simple approach. We have a mean field, and the idea came in the famous work of Anderson and Weiss, and we have simply generalized this technique. Of course, it's not so simple as some algebraic work, but finally we came to a formula, in which we have the quantities which have been already mentioned in the theory of Anderson-Weiss. We have the second moment, and we have some spectral density function. This is Anderson-Weiss theory, and the difference is only that our spectral density function, which we can numerically calculate, is rather difficult, and it depends both on the rotational frequency and also on the correlation time. It means you have not to understand how this formula has been calculated. You can also understand we have now a formula in which we can play with a magic angle spinning frequency, and we can study the influence of the thermal motion, and we simply describe the thermal motion by a single correlation time. Of course, we can improve this model, but the idea is to have two quantities, and we can play with these quantities. And now the situation is rather simple. Of course, we compare with the result of the Anderson-Weiss theory. This is also nicely described in the book of Abraham. And then you see this fundamental formula, which is used in order to understand the line shape in NMR and also in EPR in terms of the correlation time. You see this formula. If you have a very long correlation time, you can make an expansion of this formula, and you have an approximation as a Gaussian line shape. This is coming from this Anderson-Weiss theory. Otherwise, you cannot predict in general a Gaussian line shape in NMR. This is only the result of this mean field approach. Very long correlation time, you can simply make an expansion, you find a Gaussian line shape, and if you have a very fast relaxation, it means relaxation time towards t with respect to the second moment. This is nicely described in the textbook, in the famous textbook by Professor Czichik and others. You have a Lorentzian line shape, and the line shape depends on the correlation time and the second moment. This is a simple approximation, but in many cases it holds. And also this simple theory can be applied now for magic angle spinning in order to have a first influence. The problem is in our field that we have a residual line width in these cases, which is depending on the distribution, it means on the strength of the inhomogeneous field. Now I will show you an example in order to understand what happens. I mentioned the following. We have a correlation time which is essential for magic angle spinning. This is this quantity. And we have a correlation time which you can correctly determine if you make a very, very detailed relaxation measurements. This is well known from Professor Czichik. You can measure relaxation times, T1 and T2, and you can estimate a correlation time. In the case of the relaxation, this correlation time, of course, is related with a microscopic behavior. It means with changes in the orientations in the nanoscale. If you compare, and I repeat what I have already explained, the correlation time, which is essential if you have motions in case of NMR, is not related with this local correlation time, but is related with the time in which the molecule is flying or transported or jumping in a particle which has a size of about 1 to 2 micrometers. It means you have a correlation time NMR. This is a physical interesting point. It's on the nanometer scale, and you have a correlation time which describes formally our experiments. This is micrometer, and which has in fact no physical meaning, but it's only a time to understand the averaging process in this incoherent motion. And now compare. We have made a very careful analysis. This is not important. You see the relaxation times of these molecules adsorbed in zeolites, and you see the measurements at two different frequencies. One frequency is 500 megahertz proton NMR. Another frequency is 100 megahertz, and everybody who has very carefully studied the book of Professor Czichik understands now that from these two curves we can very precisely estimate whether our relaxation mechanism is described by a correlation time on the local scale. And using this information, we have this quantity, we have estimated the correlation time from our NMR measurements, relaxation, and you see this is in relation with jump-like motions or with motions in the scale of nanometers. Otherwise, we have used the sidebands in our MRS spectra to estimate this correlation time, which is useful to describe the influence of the thermal motion on the resolution in our MRS spectra. And we have estimated a correlation time, which is not a real correlation time, but some time constant, which is in the order of magnitude of some milliseconds. And you see now the different time scales. And what we always try is to relate these both quantities with this famous Einstein formula, squared of displacement. And we have the following situation. On the left case, we have motion of the particle, which is related with the size of these grains, which, as I already told, in this heterogeneous system, also in biological, can be estimated in the size of some micrometers. And if we put in this quantity, you see the difference of this correlation times on the right side, a real microscopic effect. On the left side, in averaging process, in case of our local field, it's just in relation between the different length scales, size of particle, the size of this nano volume. Means we well understand now the process of averaging. It's not the local motion, but it's the motion of the particle which is necessary in order to transfer, in order to spring from one point to the one end of this microscopic particle to the other end. It means we have now a good understanding of the time scales, and you see that just the relation between the correlation time which we have measured is in coherence with the nanometer scale, local, and this particle scale which is related to the size of our systems. It means we understand at least now the physical process of the averaging, and we understand why we have a resolution, a better resolution, although we have already a thermal motion. There's a first paper which appeared in 1917. This was the work of Doskochilova and Schneider in Prague, and they have shown in a first experiment they got a better resolution if they are using simple magic angle spanning. Nobody understood why they got a relation, because the system was already mobile. And everybody, in terms of this, all these quantum measurement effects in multi-pulse experiment and also in these modern techniques, why they got a resolution. The situation is quite clear. They had such an inhomogeneous field, and they could average over the distances, not in the nanometer scale, but in the micrometer scale. Now the situation is completely clear, and now we also understand the possibilities and the limitations which we combine these techniques with our pulse field rate techniques. It means the first idea was to understand the physics of this averaging process. I show you again the theory. This is not so important. We have, of course, tried to improve the interpretation by using this famous Torrey model in the physics, which has been proposed already in the 60s. Torrey, it means this is the translational motions. We have not a motion with small steps, but if we have a jump-like motion. The molecule stands and jumps, and the memory between these both processes is lost. This is the so-called Torrey model of lattice diffusion in solids, but it's very well, it can be applied to our system. It means we have also a quantitative picture. Now coming to the diffusion. Of course, you know the geometry. We have, as Professor Cicic had mentioned in this morning already, we have laboratory frames. This is Z, X, Y. We have an axis of rotation. This is shown here. This is our rotational axis. and we have a certain angle between the direction of the external DC field, means constant field, and the sample rotation axis. This is well known. This is the geometry, and if you consider now the coordinates in the rotating frame, of course we have this axis is the axis of rotation, and we have two directions which are perpendicular to the axis of rotation. This is the simple geometry we have, but now we have to understand how we can solve the problem if we apply gradient fields along the axis of rotation and perpendicular. It means we solve our problem in a very well-known way. We use the so-called Euler angle. You know Euler. He was in Petersburg. He founded the Russian Academy of Science. It's a very famous mathematician from Basel and from Germany and from Switzerland in particular. It's a very famous person, and we have also a good Euler program with our dear students from St. Petersburg, aspirants, and so on. And if you use the Euler angles, the situation is rather clear. Don't forget, please, this formula. I only would like to show you the following. You may have a copy of my presentation. We have, in this case, to use a very simple approach, which has been already proposed by Spies, Blümich, and Scholz. And this approach is simply based on the fact that our gradient field, which we apply by external coils, is a tensor. It means if we treat in an adequate way our problem, we have to take into account that our gradient is a tensor. We have to play with the tensor. And the result of this play is the following. We need only one component. We need only the Z component in this tensor, because the external field is directed along the Z component of our laboratory frame. And we have now to transform the gradients coming from the different components you see into the rotating frame. The formula is here. We have to calculate the product between this tensor and this vector in order to come to the effective rotating field. Effective means we are only interested on the component of this gradient field along the axis of rotation. And now look what happens. We can calculate, and if we, for instance, apply only one gradient, it means one coil in one direction, we have three different components in our field. It means we have a gradient which is time dependent. And this time dependent of the local field, of this gradient field is very disadvantageous, because we need a constant gradient along the axis of rotation. And this is also physics. It's a very simple physics, and forget please that the mathematical formula are a little bit more complicated. It means we can play to have external field which is well defined, and we can arrange the external gradient field in such a way that finally we have only one component of this external field which is just along the axis of rotation. This is also physics behind this combination, and now I will show you how we have arranged. What I have mentioned is shown here. We have this axis of rotations. This is here along this magic axis, and we have further components which you see, which are rotating, which are of no interest for our experiment. The situation is now physically completely clear, and what we have to do, we have only to use certain angles and certain quantities of the field in order to come to a situation which is finally very useful. And the solution of the problem is the following. This is a commercial solution, and the solution means we have not only one coil for producing the gradient of the field for diffusion measurement, but we have to superimpose 3 different fields, 3 different gradient fields, in order to have finally only one component of the gradient field along the axis of rotation. This is a very simple solution. I know that Varian already offers such a procedure, but not in a suitable way for our purposes. But in any case, this is in principle a well-known solution. It's not very intelligent. This is some practical solution which is useful if we consider all the work size of application. You see also Professor Karger and other people contributing, in particular my former PhD student Apambe. Now we have 3 different coils, and if you're using these coils and the arrangement of certain Euler angles, it is not so interesting for you. We have finally this very simple formula. It means we have a gradient of the pulsed field gradient which has just one component along the axis of rotation. And you see, this is a very nicely defined situation, and we can now play with this problem. You see here's the formula. Please forget this problem. It means the final conclusion, we create a gradient along the rotor axis. It means we have a magic angle gradient which is combined with magic angle rotation. This is a clear physical picture which I can see, and now we have the following situation. So you see now the rotating sample, and of course it's a little bit more complicated. We have to realize this magic angle solutions. This is one problem, and we have to check very carefully the gradient coils for these measurements in order finally to have such a situation which is expressed by this picture. You see on the left side, this is a picture to show the magic angle spinning, the gradient coil, the magic angle, and the rotational frequency. Here you see the pulse program, which is used for pulse field and diffusion measurement. This pulse program you know very well from each textbook. This is the simple program in which you have a so-called stimulated echo. It means you have a pulse program which is well known from the literature, and you use now the fact that we can define the gradient. It means the pulse field gradient. This is shape as used in structural analysis in biological system. We have a shape gradient in order to have a mostly or approximately rectangular distribution of the field. This is well known for the application of NMR in biological systems. We have this positive or negative gradient. We have the pulse width, and we have the distance. And the most important is this quantity delta. This is so-called diffusion time, and you use the famous formula which is normally applied in case of diffusion measurement. You have the diffusion constant, you have some quantities, the gradient, the width of the pulse, and we have this quantity diffusion time. If we have small times, of course we have to take into account the pulse width, and we have also to count the distance. This is the distance which is used. It means the distance between the high frequency pulses and the radio frequency pulses and the pulse magnetic field. This is standard techniques. This is the techniques which has first time proposed by Stejskal. It's a famous contribution, and then generalized in many applications. You can use this formula, and the most important is the following. You can now study different systems, and you now understand what is the role of the thermal motion in competition with a magic angle spinning, and you have to take care. In some cases, you have to spin with high frequency. In other cases, if you have an internal motion, which you should control step by step, you can also apply magic angle spinning with low frequencies. This is now completely understood in terms of the influence of thermal motion. And finally, you see that we can study the diffusion processes for each group in our systems. We can have a resolved study of the diffusion processes. Resolved, it means to several groups of molecules occurs in the same system, which are of practical and theoretical interest. This is the advantage of these techniques, and you see the technique is not so complicated, but it's also not very simple. We have the opportunity to use this in a high field spectrometer with a frequency of 750 megahertz. We can use the gradient coil systems, 3 coils, and finally, of course, we have about 60 amperes of the current in each of these coils. It means with respect to high field measurement, 750 megahertz, it's already a technical problem, but you know the same situation in other cases. And finally, we can, this is our high field machine, and we can use magic angle spinning in case of NMR. And you see the test systems are lipid water systems. This is the work of my former PhD student and Doctor of Science. And you see we have stimulated echo for these systems. It means we can study the diffusion processes in different parts of these samples. And you see these are different groups which are interesting, and I cannot make a further inspection of this system. It means we can study lipid signals, for instance, besides the other constituent. It means this is, I think, a good progress to understand the dynamics in these very complex systems, because we can now study the dynamics with respect to the spectral resolution, and we have no problems with sideband and other problems which will influence our system. Conclusions: pulse field gradient in combination with MRS can be realized by using the micro-imaging device. We can have certain fields which are suitable for our measurement, 2.6 Tesla per meter, and we can use the combination of these techniques with the advantages of solid-state NMR. And of course, the applications which I have only mentioned briefly: diffusion process in membrane systems, in zeolites, and other microporous materials. And some applications are also devoted to a matching in rotating system, but I will not touch this latter problem. Thank you very much for your attention.
Thank you for your nice talk. Yeah, so I just have a small question. Because you just explained the reason why we could do magic angle HR mass in a magic angle spinning situation. I just wonder if you put a material inside the rotor, you spin that, you create a centrifugation of the material. So when you measure the diffusion process of anything inside.
Yes. You are completely right. I did not mention the background of this technique. Of course, the sample preparation in our case is the most important case. We have well-defined tubes, but we have to seal off under vacuum conditions. It means we cannot put simply in the rotor system our material. We have to create certain tubes which still allow rotation and which are sealed off in vacuum, and our systems are treated in by means of vacuum technique, also techniques which are suitable for biological applications. And of course, your question is directed to the following question. What would appear if you have a rotating sample and if you have a speed of, say, 10, 15 kilohertz? Have we any change, in particular in the biological material, and a redistribution of the material and the influence on the structure? This is a very important question, but we have answered this question by using tomography. It means we have studied the distribution of the material by means of tomography, and we could show that under these conditions, which we have, and we do not spin higher than 10, 15 kilohertz, we have no influence of the internal structures. Very interesting and very surprising, because if you calculate the forces due to rotations, these are appreciable forces. But if you spin carefully at this, it's not as an influence. It's our experience. It means we can use these techniques also to study some flexible and some mobile structures. This is the answer which we can. Of course, we cannot spin as nowadays available 60 or 70 kilohertz. This is impossible. And it's sufficient because we have internal mobility, and this was the first part of my lecture. We have internal mobility, and now we have to play a little bit with the internal mobility, with the rotational frequency, in order to achieve the optimum conditions. Optimum is like something like 5 to 10 kilohertz, but not higher. In other case, you will have a problem. And it has been shown by Spies. He has treated this problem. He has applications, and he has internal holes, and completely your structure is destroyed.
Thank you.
You can be safe under these conditions. Yes.
When you talk about the absorption, which should slow down the diffusion,
yes.
Do you mean some sort of a specific interaction between the molecule and the surface, or just the steric problems the molecule has in order to go from one void space into the other channel?
This is a very complex phenomenon. It depends on the structure of system. If you have well-defined cages, and which have an internal structure, say a distance of 1 nanometer, yes, or several angstrom, you have a jump-like motion. If you have a system like silica alumina, then you have a surface. Of course, the motion is not jump-like. This is a combination between reorientation and jump-like motion. It's very difficult. You have to take care of these different processes. My approach, which I have presented, is a simplified approach in order to have the order of magnitude. But to go into more detail, you have to carefully investigate it, also selective measurements of relaxation time in order to find out the process. I can only tell you, in most of our porous systems, including MOFs, including zeolites, including such opal systems, we have a motion which is not the Debye diffusion, but it's something like a jump model. It means the lattice diffusion. This is our personal information, but of course we have to take care of this.
So what holds the butane on the surface? Just the van der Waals interactions?
Yes, this is a van der Waals interaction, but it's also the coupling between for instance, we have on the surface we have atoms like we can introduce sodium, or we have the aluminum or the silicon. We have some interactions between the double bond systems of the molecule butane and the surface. I mean, we have differences. If you have the different base, it means butane 1 or trans or cis butane, we have an interaction between the double bond systems. It means pi and sigma bonds and the surface sides. It's not only the steric influence, but also some influence due to the
Thank you.
Yes. Why do you present two variants of this dependence? Oh, I think it's sufficient only left. Yes. You see, sufficient and necessary is left. Yes. This is the only physical truth. Yeah. But if you normally, the people discuss in the publication the dependence on G, and this is completely wrong, because you see this is not a straight line, this is not such, this is a much more complicated situation. It's only a warning that you should very carefully treat the experiment, as you better know than myself. Yes. Thank you.